The next topic we want to take a look at is the Cisco Unified Wireless Network Architecture, and we're going to look at this in two parts. So to begin with, it's first important to understand the concept of switched VLANs, VLAN trunking protocol, and .1Q or 802.1Q specification for multiple VLANs over a trunk. So you should be familiar with this already. Not that you necessarily have to be taking this class to get your CCNA wireless certification, but I should note that if you are taking it to get your CCNA wireless certification, you really first need to have your CCNA certification. And for lack of a better term, this is really your CCNA routing and switching certification. Before, you can still go take the CCNA wireless, but you won't necessarily be certified in wireless until you've also already taken and passed the CCNA exam. Okay, so hopefully you already have a bit of an understanding, but if you don't, we will be going over not only now conceptually, but also in a moment, really in a module or two, when we begin actually looking at the interfaces of our AP and our wireless LAN controller. We're also going to take a look at our switch and go ahead and create our VLANs. Okay, so our virtual local area networks. So if you already understand the concept of a virtual local area network or a VLAN, this is essentially creating in a switched environment separate layer 3 and therefore separate, not necessarily layer therefore, but also separate layer 2 broadcast domains. The idea of these can be extended out into the wireless domain. So to begin with, let's just say we have this example of 3 switches. We have a single cable. Yes, it could be multiple cables, but just for the sake of simplicity, we have a single cable between switch number 1, 2, and 3, and the switch between, the cable between switch 1 and switch 2, and the Ethernet cable between switch 2 and switch 3, the ports that they are plugged into on those switches are configured for trunking. The idea of trunking is that we're not only sending an 802.3 Ethernet frame with an 802.3 Ethernet header, but we're also adding on an additional header called a trunking header. And there are, Cisco proprietary ones known as ISL, inner switch link, but the industry standard is what almost everyone, including Cisco, recommends and uses in today's environments, and that is the colloquially referred to as .1Q, but properly referred to as 802.1Q trunking protocol or specification by the IEEE. So the 802.1Q protocol specifies that there will be an additional header that will consist of the VLAN ID as well as some quality of service bits that we won't really get into right now, and that there's also something called a native VLAN. A native VLAN is essentially a non-tagged or does not have that additional .1Q header on top of it. So the native VLAN is essentially just a raw Ethernet header, just a standard Ethernet frame. There's always going to be a native VLAN and then additional VLANs that are allowed to go over the trunk. And basically we configure on either side of the trunk on the switch ports, we say which VLANs are allowed to propagate over that trunk link. Okay, and then when the switch receives an Ethernet frame with a .1Q header, it looks in the VLAN ID header field and it says, hey, I see VLAN ID 40, but I was only allowed to have the native VLAN of 1, which is untagged, VLAN 20, and VLAN 10. So I'm going to drop that frame. Or I see a frame for VLAN ID 20. I'm allowed to let that VLAN pass. So I'm going to take that information, decapsulate the 802.1Q VLAN header, and I'm going to pass that information on to the particular virtual LAN of 20, or I could call it support if I wanted to give it a name. but the ID, the number, is what's most important. With wireless, what we do is it's the job of the access point in autonomous mode, or as we're about to take a look, the job of something called the wireless LAN controller in lightweight mode. It's the job of those two devices, depending on which modes we're operating at, to map VLANs from the 802.3 wired side to the proper SSIDs on the wireless side. Okay? So in wired, we just said how VLANs were separate broadcast domains. Okay? Now, that might be true in a wired environment, but in a wireless environment, remember, anything that is transmitted in wireless is going to and have to be heard by everyone. So in the sense that I might think of a VLAN 10 for sales or a VLAN 20 for support as a separate broadcast domain in a wired environment, that concept does not hold true when I'm looking at a wireless environment. If someone on the SSID of sales goes to send a frame to another, or let's just say even goes to send a broadcast, an ARP, it's not only going to be heard by every client that is joined to the sales domain or the sales wireless LAN, the sales SSID, but it's going to be heard by everyone in that same frequency for a given access point association. So even people in other VLANs will hear that wireless management frame, basically that I'm about to send the traffic. Now, the encryption mechanisms, and we haven't even begun to get into security mechanisms, authentication and encryption, and we will do that in depth later, but we could just go ahead and say that assuming we do have encryption on our given SSIDs, they are probably going to be different authentication and different encryption per SSID. So it doesn't mean that the person over in support can listen to all the data that's being sent on the SSID of sales. In fact, it doesn't even mean that anyone else in the sales SSID can listen to the data, because I'm actually going to have an encrypted data sent just from my laptop over to the access point or possibly over to the controller. And nobody else is going to be able to decrypt that data. What it does mean is that everyone will have to listen to the management frame. And even while I'm sending my data, nobody else will be able to send any information, right? So in that sense, the broadcasts are not isolated. Nobody else may hear my data. They may not even see my ARP request. But the point is that everyone else will have to basically be quiet, shut their mouths, wait their turn while I'm sending. Okay. And if it's in the sense like a management frame, they simply discard it if it's not intended for them. That's the specification. Obviously, there can be rogue clients that are trying to listen to all those management frames. We do have the ability to deal with management frame protection, that 802.11 spec there. I believe it was 802.11K that we talked about, but we'll talk about that more in depth later. But right now, we're just trying to draw the conceptual distinction of a broadcast domain in wired, not necessarily having the same functionality in wireless. But at any rate, we have the SSID for sales propagated out from the AP, and we have the SSID for support, and we have the SSID for guest, just as three, example SSIDs or three example wireless LANs. Now, I drew them as different colors, and that might indicate to you, because I've used different colors in the past for different frequency or different channels, I'm not really indicating different channels here. What I'm indicating is three separate SSIDs that are all on the same channel being sent out from the same AP. I only use different colors to indicate the different SSID, the different wireless LAN. So all three of these SSID, or all three of these wireless LANs, we would say that we have three wireless LANs, sales, support, and guest. They're all on the same channel being broadcast by the AP. Okay, the difference is that they have different probably encryption mechanisms. They certainly have different B or MB SSID MAC addresses for the identification of the access point, who to send a frame to when trying to transmit to the distribution system. And the AP, or as we'll find out later, the WLC, the WLC, the wireless LAN controller, will do the mapping. In fact, we call these dynamic interfaces on the wireless LAN controller because they are dynamically mapped between a SSID and a VLAN. So it's the job of the AP, or it's the job of the wireless LAN controller, if we have one of those, to map traffic coming in from SSID sales to to VLAN 10. So essentially we take and we'll go through this a little more later, but we decapsulate. We already talked about the traversal of a frame from wireless to wired. We're now just adding one extra step. We're taking that wireless 802.11 header, stripping it off at layer 2, leaving layer 3 to layer 7 not touched, and then we're putting on not only an 802.3 Ethernet header, but we're adding on an additional 802.1Q header that says, hey, if it came from the wireless SSID of sales, then strip that wireless header, add the 802.3 Ethernet header and 802.1Q trunk to indicate VLAN 10. So send that across a trunked port from my AP or probably from my wireless LAN controller, and send that into the trunked VLAN of VLAN 10. So that when it gets into the switch, whether it goes to this switch, it would actually be sent to all switches if it was a broadcast. If it was a specific frame, then it would go to the MAC address where that particular client lived. Maybe it lived off of switch number 2, and it would be sent on to that particular client off of switch 2 or off of switch 3 or wherever that MAC address for that destination address happened to ultimately be. But it's the job of the AP or the wireless LAN controller, as we're about to talk about, to map wireless LAN SSIDs to 802.1Q trunked VLANs. So let's actually take a look at the case for centralization. If we only have 2 or 3 access points, then it's probably not going to be, I would say, really if you have 2, it's not going to be too enticing. Maybe if you have 3 APs, it's not going to be too enticing to have some sort of centralization. It's not that big of a deal. I'll simply go and configure anything that I want to configure on each access point, and I'll save myself some money. But when all of a sudden I begin to get, let's say I have, 8, or let's say each one of these represents 5 access points. So I have 5, 5, 5, 5. I've got 20 hanging off this switch. I've got 20 more. I've got 40 access points. All of a sudden, I'm going to realize not only doing my initial configuration and deployment, but making any significant changes to these access points requires going out and touching 20 or 40 different devices. We bring in the possibility for human error. We introduce that, as well as we just create a lot of cumbersome work and a lot more administration overhead. And again, as that administration overhead increases, we really don't want to minimize. We really do have the introduction of human error into that. So I might configure something wrong on 2 or even just 1 AP, and it functions differently in one part of the building than it does every other. So this is where we have in the past, really right around 2004, 2005 was when the push by Cisco and really the industry to centralize control of wireless access points began to appear. And so we have what are called wireless LAN controllers, WLC, or sometime I'll refer to them as WLCs. Okay, a wireless LAN controller is a centralized point of communication for a series of given access points. It can control a number of access points that have the same or similar characteristics configured on them or pushed out to them. And it can even control multiple access points that have different configurations pushed out to them. So I can use the wireless LAN controller to create essentially groups of configurations where I'll push different configurations out to different APs. each wireless LAN controller is going to really have a limited number of APs that it can control. And we'll take a look at some of those specific characteristics because just like we looked at some of the antennas, and we will look at some of the access points and some of the wireless LAN controllers, Cisco is going to want you to be familiar with some of those characteristics. And it's kind of hard to tell which ones they're going to want you to know for the exam. They kind of could want you to know any of them. So you're going to have to memorize, a few key characteristics of some of these devices. Wireless is kind of a very device-specific type of understanding of deployment. It's not just like a, necessarily a switch or a router where even though they have different capabilities, they can perform a lot of the same functions. So at any rate, I guess the argument could be made for either. So we have these centralized controllers. Now what's actually going to happen, and we're going to take a look at this more as we go on, but not only are these access points going to form associations to, and we're going to look at exactly how that association pairing is done in part 2 of this unified wireless network architecture module, or next module rather. But not only do they make associations and join into those wireless LAN controllers, but all the data, believe it or not, from these access points is actually going to be encrypted and sent encrypted over the wire back to these wireless LAN controllers. And it will be the wireless LAN controller's responsibility to send that data out onto the distribution system, out onto the wired Ethernet network. It will be the wireless LAN controller's responsibility to decrypt client data. So we had just previously talked about how, let's say, for instance, a wireless client sends traffic in the SSID of sales over to the AP. The AP will then tunnel that through a DTLS, a transport layer security, basically SSL version 3.1 really, encrypted tunnel back to the wireless LAN controller, which is not pictured here yet. I'll have another one that shows it. And it will be the wireless LAN controller's job to decapsulate that 802.11 traffic and then send that traffic onto the 802.3 infrastructure using the proper VLAN ID, using the proper .1Q tagged VLAN ID or trunk ID. Okay, so how will the traffic get? We're going to talk a lot more, but how will the traffic get from a access point still using 802.11 headers over a wired infrastructure? Well, it's going to be encapsulated. Okay, it's going to be encapsulated and sent. We're going to talk more about that in a little bit, so I'll come back to that. But I just wanted to bring into understanding that all that data from the clients to the AP, it's almost like the AP. In fact, that's why it's called a lightweight access point, because it really just becomes almost just a radio at that point. There's configuration pushed down from the wireless LAN controller, but it almost just becomes, for lack of a better term, a dumb radio. Okay, it doesn't have a lot of distributed intelligence. Instead, it's just sending signals, receiving signals, and it's sending everything that it gets onto the wireless LAN controller, and the wireless LAN controller becomes the brain. Now, as we begin to grow even larger in operation, and now each of these that represented 5, so I had 20, 40, 60, 80, I have 160 APs here spread out over multiple wireless LAN controllers. I have, at least here just in this picture, 8 wireless LAN controllers. Maybe I also have remote branch offices with wireless LAN controllers. Maybe I have a couple hundred or 1,000 APs with tens or hundreds of wireless LAN controllers. Then all of a sudden I begin to realize it's a lot of work to just configure all the wireless LAN controllers. And you might say, well, nobody has networks that big. Well, sure, they absolutely do, of wireless networks that big. Think of a multinational company with a couple 100,000 employees, and buildings all over, they want to centralize the control of these wireless networks. And you better believe they're all going to have wireless networks in today's, enterprise environment. They're going to want to centralize these even more. So we're still going to use wireless LAN controllers. All the data is still going to be captured by an individual client, pushed down, tunneled through the AP to the WILC, to the wireless LAN controller, and then out to the distribution system or wired network. I keep saying distribution system so that it will really gel in your mind what a DS is. So they'll still be sent, the traffic will still be sent to the 802.3 Ethernet network through the WILC, through the wireless LAN controller, and they will not be sent up, the data will not be sent up to this centralized, what we call WCS, or wireless control system. It's just that the WCS will be a centralized point of management for all of my wireless LAN controllers. So the WCS will really contain a number of templates that we'll use to push configurations down to one or multiple wireless LAN controllers, and those will in turn push their configurations down based on what I did on the WCS, push those down to the access point, the lightweight access point. Okay? And then as I grow even larger in scale, I might actually have multiple WCS servers. So maybe for each country that I had a presence in, I might have 50 offices, maybe, just depending on how many APs, how many wireless LAN controllers you have, maybe I'm going to have 2 WCS servers for each country, and I'm going to have a presence in 4 countries, so I have 8 WCS servers, and I want to be able to really then see all my WCS servers centralized. There's a product called WCS Navigator where I can look at and configure each of my WCS servers. It's really just another instance of WCS, but it's more just an aggregator instance. Okay. So the idea of centralized control, early IPs were all autonomous. With the Cisco Unified Wireless Network, we have the lightweight access point managed with a controller. Almost all configuration is either done on the WILC or it's done, as I mentioned, on the WCS, the wireless control system. There's 5 primary functional areas. We have wireless clients, access points, network unification as a whole, that's the wireless LAN controller, network management, and even network services. We're going to unpack all these a lot more. I'm kind of going over a bit of a higher overview of the entire unified wireless network architecture. Dealing with clients, we have different clients, and we're going to be taking a look at some of these, such as the, probably tomorrow, or for those in the recording, in about, I'd say, 2 to 3 modules. For the wireless clients, we have the Cisco AnyConnect software. Now, this is not just the SSL VPN AnyConnect that most of you have used, but Cisco's AnyConnect client actually extends out to many more functional areas than that. The one that we'll be looking at is the Network Access Manager, or NAM, portion of that we can use to join and control our wired and wireless networks, and specifically authentication and encryption with those. We'll be taking a look at it briefly, probably in a couple modules, and then we'll also be taking a look at it again a bit more heavily when we talk about security, authentication, and encryption. There's also the Cisco Secure Services Client, something else that can provide different measures of security, really not anything more. AnyConnect is what most people use these days. There is something called, and this is not a particular client, this is a program, something called Cisco Compatible Extension Program, or CCX. And this is basically a software development kit, or SDK, that individual wireless manufacturers can participate in, and I should note that many vendors do. And by supporting different versions, as we go along, we have newer versions of this. Excuse me, and the newer versions can support newer, better things. We're actually going to take a look at a matrix of all the CCX, the Cisco compatible extensions out there from version 1 to the current version 5 and see what the differences in those are. Most notably, we'll look at some of the differences in version 3, 4, and 5, the latest ones. And because every version is going to support everything that the previous did, but add a few additional things. But anyhow, the manufacturers of wireless cards, the vendors, Intel wireless cards, Netgear, actually whatever chip manufacturers, Broadcom, that might create wireless cards and put them in devices such as, iPhones, Android, laptops, whatever, they can participate. And like I said, many do in this program. And the idea is that, well, the standards bodies of 802.11 don't move fast enough. It's great that they're there. They absolutely need to be there. But they are rather slow moving. That's with intention. And Cisco participates on many of the 802.x boards, or even IEEE boards in general. Writes and participates a lot of the RFCs out there. But the thing is that they need to be intentionally slow and make sure that they cover every single base, and that it's something that every manufacturer can participate in. That's the idea of an open standard. It's not proprietary. It's not locked into one manufacturer. The problem is that they don't necessarily address the needs of the consumers fast enough. There's a reason for them, but they can't necessarily keep up with demand. Demand might outpace the actual ratification of protocols. And so it almost always is private industry that goes and creates the idea. And let's say something that we'll talk about with Cisco compatible extensions known as fast roaming, available in CCX version 5. Not only did Cisco come up with something that they could do as long as vendor X participated in CCX, the Cisco compatible extension program, they could do before a standard came out, but they would create an idea, basically say, hey, as long as everyone participates in this particular Cisco proprietary extension, then it's going to work great. But they also then go and use those proprietary solutions to propose open standards, and they work towards those open standards with other vendors. It just takes a while to get those into, actual ratification. So for instance, something called fast roaming is an 802.11 IEEE proposal. It just hasn't been ratified yet. Until it's ratified, consumers and enterprise customers still demand this type of functionality. They need it, especially with voice and video type entities. Let's say a wireless phone, or a Vocera wireless badge in a healthcare industry where lives are literally on the line, and someone's literally running between halls in a hospital emergency type environment. And the words that they're speaking that are being transmitted over this wireless are absolutely critical to someone's life being protected. Fast roaming between these access points is critical. So this is where demand outpaces the ratification. So I'm not trying to, kind of advocate or really say anything pro or against Cisco's proprietary solutions. Every vendor does it. I think it's a good thing because they then go and turn those into open standards. But anyhow, the idea is that these are proprietary extensions to a wireless network that haven't yet been ratified into an open standard, but nevertheless we can still benefit from today, provided that manufacturer X supports them. Cisco compatible extensions are something that when we look at the Wireshark packet capture, we're actually going to see that this information is sent in a probe request, and we're going to see whether or not a given client supports what version of Cisco compatible extensions. And so the AP then knows what new features that are above and beyond the actual open standards, 802.11 open standards, can be tagged on can be used. You know, can we use fast roaming? Can we use different types of authentication than what the standard calls for? And then we also have the built-in OS-dependent clients. So for instance, in Linux, we have something called Network Manager is a very common one. In Mac OS X, and we'll take a look at some of these. I'll bring up a Windows 7 machine, and I'll bring up a Mac, and we'll just take a look real briefly in the next module, or right after the next module, at the actual built-in wireless clients, as well as taking a look at the Cisco AnyConnect software, which can be deployed on Mac, Linux, or Windows. Now we want to take a look at LWAP and CAPWAP. So LWAP is the lightweight access point protocol, and CAPWAP is the control and provisioning wireless access protocol. The idea, or control and provisioning wireless access points, sorry. But the idea, and CAPWAP is something that has taken over and superseded LWAP. The idea of LWAP and then CAPWAP was to relay information from the access point to the wireless LAN controller about a number of things, such as coverage, such as any interference that the access point might be experiencing, the actual client data about association, encrypted communication between those, between the access point and the wireless LAN controller. All the client data is also sent inside these LWAP or CAPWAP frame headers, LWAP being the older standard, CAPWAP being the newer standard. The client data travels from that wireless space to the AP and then encrypted in tunnel, something called DTLS, through through the AP to the wireless LAN controller and then out to the rest of the network. Okay. When the client data is encapsulated in this CAPWAP header, you're going to have information about the received signal strength indicator, the RSSI, and the signal to noise ratio. So the wireless LAN controller gets really a full picture, not only of what the AP is seeing, but what the client is seeing in the network as well. Creates a centralized brain, if you will. Some differences between LWAP and CAPWAP. So really they have the same primary function. CAPWAP is just a newer protocol and improved on a lot of this beginnings of LWAP. So LWAP was used primarily from 2000, I'd say 2004, 2005, on up till about 2009 when CAPWAP took over. So they both use UDP ports. LWAP uses 12.222 and 12.223. So 12.222 is the data channel, and 12.223 is the actual control channel. Sort of like FTP uses a data channel and a control channel. CAPWAP uses UDP 5246 and 5247 for the same data and control respectively. CAPWAP enables PMTU discovery, which is path MTU, so maximum transmission unit. Basically, discovering along the way through ICMP messages what's the maximum transmission unit that can be sent. Because if for some reason we have fragmentation, we know that that slows everything down. With path MTU discovery, assuming that there aren't blocks on ACLs or firewalls prohibiting certain ICMP control messages or ICMP probe messages, then I have the ability to scale back my MSS, my maximum segment size, or basically the size of the data payload that I'm sending, so as to avoid any fragmentation issues. CAPWAP encrypts the data channel via DTLS, okay, or datagram transport layer security. Transport layer security is really SSL version 3.1. So we had SSL version 1, 2, and 3, and then when we got to 3.1, we decided to call it something different, TLS, to really kind of reinvent itself because it really had undergone such a change by then. So at any rate, LWAP encrypted the initial communications, the control, but it didn't encrypt the data. CAPWAP encrypts the data. CAPWAP supports IPv4 and v6. LWAP only supported IPv4. CAPWAP also supports NAT traversal, very important, over firewalls or really just any sort of NAT device. CAPWAP also uses a different option than LWAP did for DHCP-based AP association. We're going to talk about how that works in the next section. So again, we're just taking a look at something that we had already looked at before, what the MAC addresses are, the difference being that all of a sudden now there is a encryption from the AP to the WLC, to the wireless LAN controller. It's now the wireless LAN controller, not the AP, that decapsulates it basically unencrypts the datagram transport layer security, or DTLS, encrypted packet. It then decapsulates the 802.11 header, encapsulates the 802.3 header, tags on the 802.1q VLAN ID based on the SSID that the traffic had come in on, and then it sends it out to the wire. Now, with wireless LAN controllers, we have the ability to have groups of controllers, and the reason for having groups of controllers deals with something that we'll talk a lot more about called mobility groups having to deal with roaming. Okay. There's also something that we can add on, and we don't have it, we really don't need to know too much about it other than the fact that it exists, called the Mobility Services Engine, or MSE. This used to be called a location appliance, the Cisco location appliance. It's now called, it's actually a brand new device almost, but it's called the Mobility Services Engine, or MSE. This can be used for very, very granular location-based client tracking, or not only client as in laptops and smartphones. It can certainly do that, but it can also track RFID tags, radio frequency ID tags. And the ability to have, there's multiple different modes for tracking these, and we'll learn a lot more about them in the CCNP wireless site survey course, and even more in the mobility services course for wireless. But there's different modes. We can do we can basically do closest RSSI, basically, whatever AP hears a given client, because multiple APs might hear a client. Whatever hears it at the closest RSSI, we'll know it's within this general vicinity. We can grab RSSI values from 3 different APs if we have them placed close enough together, and do what's called triangulation. And then we also have the ability to set up these very, very highly precise. The site survey involves a lot more initial planning and data accumulation to set up this, essentially this grid, and we can have literally up to a 1 meter discovery, 1 meter accuracy of discovery of where any wireless device is in our entire network. The more precise measurement you need, the more access points you need. Kind of makes sense. Again, some clients might, not wireless clients, but consulting clients might say, wait a minute, you're just trying to bill me more money. But no, there's actually a reason for including more access points in even more and more. There's also something called radio resource management. We'll talk quite a bit about RRM. Radio resource management deals with a lot of different components. One of the things is dynamic channel assignments. So as a given channel becomes congested or experiences interference, we have the ability for the AP to inform the wireless LAN controller, and the wireless LAN controller in turn to inform the wireless control system, the WCS. And based on how we've configured it, if we've configured it to have a static channel, then it's not going to change. But if we've configured it to do sometimes event-driven radio resource management, and if we've configured something that we'll take a look at, we'll only take a brief look at because we only need to understand a little bit about it now, we'll take a decent in-depth look at it, something called Cisco Clean Air, then radio resource management becomes very, very useful. We're going to detect and avoid interference. We might allow our APs, based on our predetermined rules, to dynamically switch channels to another non-overlapping channel based on that interference. And we might dynamically control the transmit power. Remember, we talked about TPC. We talked about how it can be a bad thing for voice, but it can be a good thing for data. So it really just depends on the environment, if we're deploying voice and video or if we're just deploying data, and if we want to allow radio resource management to dynamically control that transmit power control, that TPC. Taking a look at the modes of wireless LAN controllers, when we were still in the olden days of LWAP protocol, we had the option of using layer 2 LWAP mode. This only dealt with MAC addresses. The access point had to be in the same layer 3 subnet or layer 2 wireless, not wireless, but VLAN, wired VLAN as the controller. Okay. Nobody uses this anymore. It's not to say that we couldn't place a controller in the same VLAN, but a lot of times it's not. Okay. What most people use is the layer 3 CAPWAP mode. Okay. Or even, LWAP supported this layer 3 mode as well. Okay. So we're not only dealing with MAC addresses, we're dealing with MAC and IP addresses between the access point and the wireless LAN controller. And of course, the protocol has to traverse subnets. And therefore, the access point has to be able to discover, broadcast, and discover across subnets. Well, we know that broadcasts do not go across subnets. The whole idea of a subnet or of a VLAN is to limit my broadcast domain. Well, we are going to take a look in the next module at how we'll overcome a layer 2 broadcast boundary, similar to how we overcome a layer 2 DHCP broadcast boundary with forwarding. So wireless LAN control, there is, we can deal with multiple networks. Okay, so first of all, an AP, we've already said, can advertise multiple SSIDs. They can be tied to different IP subnets, different 802.1q VLAN IDs. Okay, and a wireless LAN can support multiple VLANs based on the specification of the wireless LAN controller, the WILSI. APs can typically support up to 16 SSIDs. And finally, before we move into the next module, which is just a continuation of this module, just need to separate them for time, we want to take a look at some of the actual specifications or specs of these wireless LAN controllers. So let's go back to cisco.com. Okay, we'll bring up our web browser here. And we're going to go to products and services and wireless. So first of all, we probably should look at some of the different access points as well. And we will look at some of the wireless LAN controllers. A little bit later, we'll be looking at the wireless network management and things such as the wireless control system, navigator, and even, we'll also maybe take a quick peek at the mobility services engine. But for right now, let's take a look at some of our access points and wireless LAN controllers. Let's go ahead and look at the wireless LAN controllers since that's what we were beginning to talk about here. So we see that we have some very large controllers, such as the Cisco Flex 7500. We also, as a very large controller, have a wireless services module. This is known as the the capital W, lowercase I, SM, or WISM, as some people call it, version 2 for the 6500 switch. There is, so it basically, goes the 75, let's just take a look at some of these data sheets. I'll pull the 7500 Flex up, the wireless services module, the 5500 series, the 2500 series, and then the wireless controller software for an ISRG2. So here we can see, in fact, let's just go to the PDF version for each of these, because we can zoom in on some of these a little bit better. Okay, whoops. So first of all, we have our 7500 series cloud controller. This is, you're probably not going to need to know too much about this one for the exam. At any rate, we have up to 3,000 access points that we can control. So we can control multiple controllers and support up to 3,000 APs on this particular model with up to 30,000 clients. If we take a look at the 6500 WISM, we can control up to, 1,000 APs and 15,000 clients, so half the clients and 1/3 the number of APs. And it tells us the actual supervisor and versions of chassis, e-chassis or non-e-chassis with a high-speed fan, the version of iOS software that we need, and the minimum version of controller software that we need in order to use this particular controller in a 6500 series switch. And we used to be able to put these into a 7600 router as well. Not sure if the version 2 supports that. It doesn't look like it does. Or 7200 series router. So I think that's where the 7500 series cloud controller took over. The 5500 series is really the smallest that you can use for a number of the more advanced features, such as mobility anchors. Actually, I'm used to the 2100. The 25 may actually do mobility anchors as well. So the older one was 2100 series for a smaller implementation of 6 or 12 access points, and the 2500 series supports up to 50 access points and 500 clients. Okay, 802.11n ready and able to support up to 500 megabits. So remember, all the APs are sending all their data back here to the controller, and then it's sending it out. So 500 megabits might be enough, but probably for a decent larger size enterprise, that's not very much transmission at all for a lot of 802.11n clients sending data all at once. The 2500 does support clean air, the clean air technology. If we go back to the larger 5500, I believe we still do need this particular one for something that we're going to talk about later called mobility anchoring. Okay, so just keep that terminology in your mind. We'll talk a lot more about it when we talk about mobility groups. That has nothing to do with the mobility services engine. The mobility services engine is about client tracking, but when we're talking about roaming between SSIDs and between SSIDs, but between access points with the same SSID and even between controllers, we're going to talk about something called mobility groups, and you need a mobility anchor to do that. And the 5500 is the smallest one that will do that mobility anchor. So the 5500 will do up to 500 access points and up to 7,000 clients. Now the other number, if I take a look, let's see if it shows it down here. The standards that it's supporting, let's see if it shows. Yep, here we go. So it shows different part numbers, such as these are all 5508. The 8 in the number represents the number of ports. And then the next number, -12 or 25, represents that I have licenses for 12 access points, and I can get licenses in the same model, 5508, for up to 500 access points. Okay, but the 8 in the 5508 refers to the number of Ethernet ports. Now you see a few other ports here. One is going to be your console port. One is going to be what's called an out-of-band service port. We're going to talk more about those ports and show how to configure the IP addresses and what we use them for a little bit later. But the number of ports that we can use to even create Ether channel aggregation points back to the wired LAN and be able to switch a given amount of traffic back to the wired LAN. Okay, this has faster RRM updates for uninterrupted network access when roaming. It's got efficient roaming improves application performance, such as toll quality, voice, and consistent streaming of data backup and video. So there's a number of things here. Supports rogue access point detection and DOS attacks. MFP, it supports management frame protection. This certainly does support Cisco Clean Air initiative, something we'll be taking a little bit of a look at. Okay, so these are the different models and some of the different, talking points or some of the different stats. Main thing you're going to want to remember is what protocols they support. Do they support 802.11n or do they not? And all of the newer ones do. If it's something outside of the 7500 Flex series, the WISM 2, the 5508, or the 2500 series, I believe we have a 2504, and I thought we had a 2508 as well, or 2502, but we have a 2504, just 4 Ethernet ports here. If it's something outside of these, then they don't support Clean Air, and they don't support 802.11n. One other is the Service Ready Engine. So we have the wireless control software. This is really for a branch office. So we can put this software on a SRE, a Service Ready Engine, which is one of the network modules, or really called service modules. I think they have a picture of it here. They don't on this page. Okay. Anyhow, that we slide into a ISR G2 router, so a 2900 or 3900 series router. Okay, it does support 802.11n. Does it support Clean Air? It does support system-wide Clean Air through our RRM, Radio Resource Management. So those are your options for controllers. Let's also take a look while we're here at the access points. We have our 3600 series. We have the first 4x4 option. So the first antenna of Cisco's that provides 4 multiple spatially multiplexed streams. All the other antennas support 3. You see 6 connectors here. That's 3 for the 2.4 gigahertz and 3 for the 5 gigahertz range. We see some of these 3500 series and 1140 series that don't show external connectors. That's simply because it's showing you a picture of the internal antenna version. There are 3500 series APs that have external antenna, and they look pretty much just like the 1260 series. In fact, the main difference from the outside, other than the actual tag on the back, is the fact that the 1260 series just kind of has the word Cisco and the actual logo there for the Cisco San Francisco bridge as kind of just printed on the top, versus the 3500 actually has it indented into the actual metal casing. But this does have an external antenna option. I've got one here in my office. We'll be taking a look at it a little bit later. Now, one of the things that I should mention is that you need to have a 3550 or 3600 series to support Cisco Clean Air. We're going to talk more about this. What this basically is this is a silicon level ASIC specific chip that actually supports watching and listening to more frequencies than are even available in the 2.4 and 5 gigahertz 802.11 spec. So it actually watches kind of side channels, channels that are ranging up to the 2.4 or just beyond 2.4 or up to and just beyond the 5 gigahertz. It's also able to detect and recognize not only side channels, but it's also able to detect and recognize other types of 2.4 gigahertz transmissions. So for instance, it can accurately tell the difference between 802.11 and Bluetooth. It can identify the difference between Bluetooth and a microwave oven. can identify the difference between a microwave oven and some sort of analog video device, such as a baby streaming monitor. Won't say baby streaming, but it'll, say analog video. So it can actually identify some of this. It can identify the specific signature of an RF jammer, a radio frequency jammer. And it can actually intelligently inform the wireless LAN controller or wireless control system ultimately, and respond to countermeasures that those wireless LAN controller or wireless control system direct it to do in order to keep the air essentially as clean as possible, keep the clients in a as pristine of environment as possible. Again, when I think about this stuff, sometimes I'm thinking about a brand new greenfield installation at a company who owns the building. But that's not really just everyone out there. In fact, even Cisco, if you look at most of their regional sales offices, they lease space. If you're in Dallas, San Jose, RTP, Brussels, Sydney, and Bangalore, they own their buildings. And in Sao Paulo, Brazil, they own the buildings. But even Amsterdam, they own the building. But let's say Dubai, they don't own the building. In here, all sorts of different regional offices. If you go to, I don't think they own the building in Chicago. They do own the building it doesn't really matter, but many different places they've got their regional sales offices and engineer offices where they don't own the buildings and they have to share building space, and therefore they have to share airspace with other companies who have their own wireless LANs deployed and therefore compete for that airspace. And so Cisco recognized it as a problem that they have internally, and they tend to eat their own dog food, as they call it. So they make the stuff and they use the stuff themselves. They don't just preach it and sell it, but they use it. And so one of the things they ran into was, how do we keep this airspace as clean as possible? It's a good marketing term, at least. How do we keep our clients in as pristine of environment as possible? And that's really what Clean Air seeks to accomplish. And we'll look a lot more at it later, but only the 3500 and 3600 series support that. The 1140 does not. 1260 does not. Okay. By the way, I mean, if we take a look at others, there's the 1140. There's also the older 1130. The 1140 supports 802.11n. The 1130 only supports ABG. The 1260 supports 802.11n. The 1250 only supports A, B, and G. Okay? The 1040 supports 802.11n. It's a, as you go down in numbers, it's going to be a much lower level access point. It's going to not do nearly as many features, but then again, it's going to not cost near as much either. So it's a great entry level access point. Okay. And then we even have something called the Aeronet 600 for Office Extend. Now, I don't think that Cisco will test you on it, but it's certainly possible that they would ask you a few questions about their older solutions, such as their 500 series, something that used to be called used to be called their Express solution, the Cisco Wireless Express solution. It had a Express controller. It was a wireless LAN controller, but it kind of wasn't really a full-fledged wireless LAN controller. It was kind of only partial. It was like a very crippled version that didn't really have near as many features, and it also actually didn't even speak exactly the same protocols. It was kind of a cobbled together piece. And so therefore it could not communicate back with the wireless control system or with other wireless LAN controllers, such as the 2100 series or 2500 series, or even the older 4400 series or the newer 5500 series of wireless LAN controllers. So the mobility, or not the mobility, but the Wireless Control Express, the Wireless Express 500 series APs and 500 series Wireless Express controllers were kind of they were an island. They were all by themselves. They worked for a very small office, but they could not communicate back with anyone else. The new approach, so it's just important to know that those existed and that they really didn't interoperate with anything else in the enterprise. But the new way of doing it is the 600 series Office Extend, and using those in conjunction with a wireless controller software for the ISR G2. And these do allow for the newer technologies such as Client Link, something we'll talk about later, video stream, clean air, and communicating back to a WCS. Okay, so I would highly recommend that you go to Cisco.com, go to products and services, go to wireless, take a look at the View All Wireless products at the antennas, as we went over earlier today. Take a look at the access points and specifically look at each of the data sheets. Just click on and open up each of the data sheets and just get a general idea of what the different access points, different antennas, and different wireless LAN controllers have available to them on their specifications. And typically on the left here is where you can find an overview. And again, it's kind of hard to read in this font, and this is actually a graphic for some reason. So that's why if you go to the PDF, I prefer it. It's might be a graphic, but I can at least scale with a vector the actual font face, and I can highlight and copy, or at least kind of go over. I can go over some of the more important talking points and specifications of a given access point. Here's kind of the symbol we talked about earlier of the Wi-Fi Alliance. So if I take a look down at the bottom, it's going to tell me what particular, let's see, the AP may not as much. The wireless LAN controllers did. If I went back to one of the wireless LAN controllers and went down to the bottom, here we go. This shows me all the IEEE 802 standards and also what RFCs they conform to, right? Like CAPWAP, that's an industry standard. That's RFC 5415. Okay. But then when I went back to the actual AP, I see this Wi-Fi certified. Remember, this is the alliance that simply does the interoperability testing. And that's the symbol for ABGNN certified interoperability with anyone else that also displays the Wi-Fi ABGN certified logo. Okay, but I would definitely recommend going over these different data sheets and coming to know some of the differences between these APs, controllers, and antennas.